Hey, what's up guys? Welcome back to our YouTube channel. Today we're going to be exploring examples of calculus in sports.
First, we're going to be going over a related rate with a baseball run into third base.
Then we're going to do extrema of a punt.
Next, we're going to be going over a LeBron James airbound basketball shot mixed with arc length.
Then we're going to do the related rates of two runners in a football match. Soccer!
And finally, we're going to be going over Riemann sums and the MVT in a track race.
A base runner is on second base when the batter puts the ball in play. The runner is currently 30 feet away from second base and is running at a speed of 22 feet per second. Each base is 90 feet apart. At what rate is the distance between the runner and home plate changing? To start, we can draw a diagram with the base runner at point X 30 feet away from second base. Then we can show that distance A is 60 feet, which is 90 minus 30, and distance B is 90 feet. The distance between point X and home plate, or distance C, is a direct line between the two. First, we must find distance C. We can use the Pythagorean theorem to plug in distance A and B to find that distance C is equal to 108.2 feet. Next, we write down the rest of our known values. dAdt is negative 22, which is given to us in the problem. dBdt is 0, since the distance between home and third doesn't change as the runner runs towards third. Finally, dCdt is the rate we are trying to solve for. We need to use an equation that relates all variables, which here is the Pythagorean theorem. We take the derivative of this with respect to t, and we get 2a dAdt plus 2b dBdt equals 2c dCdt. We can eliminate the second term since dBdt is equal to 0, and we can cross out 2 since they're in all terms. To solve for dCdt, we plug in our known values of a, dAdt, and c, and algebraically solve for dCdt. With this, we get that the rate at which the distance between the base runner and home plate is changing at negative 12.2 feet per second.
A football player punts the ball into the air. The height of the ball can be modeled by the function h of t equals negative 5.5 t squared plus 22t plus 3. When does the ball reach a maximum? What is that maximum? What is the arc length of the football punt? Since the function is continuous on the open interval, then there exists an absolute max and min on that interval by the extreme value theorem. To find the time and height of the max value, we must take the derivative of the function. And we get h prime of t equals to negative 11t plus 22.5. Then we must set this equation equal to 0 to find the critical values. We plug the equation into the calculator to find the 0 and get t equals 2.045. Then we put that on a sign line and figure out if that is a max or min. Since h prime of t at 2.045 equals 0, and since h prime of t goes from positive to negative at 2.045, we know that is the max height. To find the max height, we plug in t equals to 2.045 into the original equation to get h equals to 26.011 feet. Finally, to find the arc length of the punt, we use the equation, which is the integral from 0 to 4.22 of the square root of 1 plus the derivative function squared. We plug in our values into a calculator to get the arc length, which is 49.413 feet. Next, we have a shooter standing at the three-point line on a basketball court, which is 23 feet and 9 inches away from the hoop that is 10 feet tall. Our player is going to shoot the ball with a release height of 7 feet and 8 inches. We know that the shooter shot the ball with perfect horizontal accuracy, which means that it is in line with the basket and cannot miss wide. The shot can be modeled by an equation which can be represented by this Taylor polynomial. T equals 10.917 minus 1.151 x minus 23 minus 0.185 x minus 23 squared over 2 factorial. Can we guarantee the ball went in?
In order to estimate the height of the ball when we reach the basket, we can use the Taylor polynomial and plug in 23.75. We get 10.001718. Now we need to figure out the maximum amount of error there could be. In other words, the most far off our Taylor estimate could be from the real life height by using the LeBron James error-bound equation. All we do is plug in our values into the LeBron James error-bound equation to find the maximum amount of error there is. We get 6.7078 times 10 to the negative 4. Now we use the estimated value from the Taylor polynomial, which is 10.001718, and add and subtract the maximum error from the LeBron James error bound equation to get the maximum interval, which is 10.00104 to 10.002389. Since the absolute farthest away the ball can be from the basket at 23 feet and 9 inches is 0.0023 feet, or 0.0276 inches above the rim, and the diameter of a basketball is 9.51 inches, we can guarantee that the ball goes in the hoop.
Green.
Next, we have two players on opposite teams running to a soccer ball that is in the corner of a soccer field. Player S is running at a rate of 7.33 feet per second, and player C is running at a rate of 11 feet per second. Player S is 50 feet away from the ball, while player C is 68 feet away from the ball. Both players are running directly towards the ball. We are trying to figure out what the rate at which the distance between the two players is changing and who gets to the ball first. First, to find the rate between the two players, we need to find the distance between them, which we use the Pythagorean theorem and plug in distance A and B to find that C is 84.404 feet. Next, we write down the rest of our known values. dA dt is 7.33 feet per second, dB dt is 11 feet per second, and dC dt is the rate that we are trying to solve for. To solve for dC dt, we need to use an equation that relates all variables, which is the Pythagorean theorem. We take the derivative, which is with respect of t. We can solve this equation plugging in values that we know to get the rate at which the distance between the players is changing is 13.24 feet per second.
To find which player gets to the ball first, all we have to use is the speed equals distance over time equation and plug in values to find the time. Player S gets to the ball in 6.82 seconds, and player C gets to the ball in only 6.18 seconds, so player C wins. Two runners are on the last stretch of a race. Runner A has conserved more energy for the last leg of the race than runner B. The closing stretch of a race is considered the last 100 feet. The velocity times of runner A and B are given in the table below, where t equals 0 is the start of the closing stretch. Using trapezoidal Riemann sums, who wins the race if runner B begins their closing stretch 1.3 seconds before runner A? What is the guaranteed acceleration of runner A? To find the winner of this race, we must find how long it takes for each runner to run the last 100 feet. Since this is a velocity timetable, we can figure out the distance covered on any time interval by using a trapezoidal Riemann sum estimate. We multiply the change in x by the average of the two y values over that step. As we add these distances together, we stop once we reach 100 feet. At 3.76 seconds, runner A finishes the closing stretch of 100 feet, and at 5.34 seconds, runner B finishes. Runner A started the closing stretch 1.3 seconds after runner B, so we add 1.3 seconds to runner A's time. Runner A wins the race. To see if runner A's acceleration ever equals 0, we want to find if the derivative of the velocity time, named f of t, will equal 0. Since the velocity time is continuous and differentiable, the mean value theorem applies. By the mean value theorem, there must exist a value c1, where f prime of c1 equals 0.4, where c1 is an element of 0 to 1.25, and another value c2, where f prime of c2 equals negative 0.12, where c2 is an element of 1.25 to 5.34. Since f of t is twice differentiable, then f prime of t is differentiable and also continuous, so the IVT applies. F prime of c1 is greater than 0, and f prime of c2 is less than 0. Therefore, by the IVT, f prime of t equals 0 for some t on the interval from c1 to c2. And since f of t has to equal 0, there must be a point t where runner A's acceleration is also equal to 0.